Okay, good evening, everyone. Welcome to the Edelstein Center's online event, which is today part of the Bar Hillel series of lectures, a series that has been carried out for about 35 years in collaboration with the Cohen Institute at Tel Aviv University and the Van Leer Jerusalem Institute. Our speaker today is Professor John Norton, who is a distinguished professor at the Department of History and Philosophy of Science of the University of Pittsburgh, where he was for many years the director of the Center for Philosophy of Science. Professor Norton wrote extensively and made influential contributions in a number of fields in the philosophy and history of science. In the history of physics, for example, he wrote especially on the history of space-time theories. And in the philosophy of physics, he wrote on the philosophy of space and time, on the foundations of quantum mechanics, and about thermodynamics and statistical mechanics, and the connection or lack of a connection between information and thermodynamic entropy. Professor Norton is also one of the leading writers on general philosophy of science, where he wrote, among other things, about causation, explaining it as part of folk science, about thought experiments, asking how they can give knowledge, can give rise to knowledge, and about ampliative reasoning, which is today's topic. John has been in Israel in the past for a number of events. So thank you very much, John, for willing to give your lecture online today on your material theory of induction. Please.
Oli, thank you very much. I was very disappointed that the lecture, I think it was scheduled for May, was cancelled. So I lost the opportunity to come and greet you all in person. I know many of you, and I would have liked to make more friendships through the visit. I'm happy to do this. It's at least some sort of connection at a time when connections are rather slender. Thank you very much, all of you, for coming, and thank you also for moving the time a little so that I didn't have to get up so terribly early in the morning. With that said, I'll get straight on with the lecture. I'm going to share my screen and then turn on the PowerPoint, and we can get going. So at this point, you should all see my screen, and give me a thumbs up if you see it. Okay, good. Okay, so my topic is the material theory of induction. And just to get us oriented, let me tell you why this is something that I care about. In my view, there is a single most important relation in, sorry, I'm just adjusting my screen. There is a single most important relation in science. It's the one that stands above everything else. And it's this one. Oops. It's this one. It's the relationship that connects the evidence for a scientific theory with the theory itself. This relationship is what makes science special. What makes science different from the many other intellectual activities in which we engage in. This is the thing that makes it such that scientific content has a preferred status for us. And the thing that does that is inductive inference. So it's very important to me that we understand how inductive inference works. It's the thing that makes science special. Now, my concern over many years is that our existing accounts of inductive inference simply aren't doing the job well enough. And after a while, I finally came to the conclusion that we'd taken a wrong step very, very early on, that the basic conception that we've been using for inductive inference is wrong. And this is the result of the ongoing confusion over exactly how we ought to think of inductive inference. So it's with that perspective in mind that I want to tell you what the main claims of this talk are going to be. There are going to be two things that I intend to establish. The first is to defend what I call the material theory of induction. The basic idea behind the material theory of induction is the following. So far, almost everywhere, and inductive inference has been warranted or validated by showing that it fits with some kind of formal schema. So if you want to know, is this a good inductive inference? Is that not a good inductive inference? You pull out your collection of templates, universal templates, and you see if there's one that fits. And if one fits, then you have a good inductive inference. If there's one that doesn't fit, then you don't. This is the way that deductive logic has been run for thousands of years, and we've tried to get this to work as well for inductive inference. My conclusion is it hasn't worked. So then how do we know which are the good inductive inferences, and how do we know which are the bad ones? Well, the warranting of an inductive inference, I say, is done by a background fact. If you want to know, is this a good inductive inference? Then you ask, what are the background facts? And do they authorize this as an inductive inference? That's the basic claim. Now, I've taken on a huge burden. I have to then go through all the various accounts of inductive inference that are in the literature and show how I'm doing a better job. Right? That's a big job. I won't try and do that in the talk today. But what I do want to do is look at just one case of that. This is the case that many of you are probably thinking of, and that is the case of Bayesian approaches to inductive inference. I'm going to argue that the Bayesian account does not supply us a universal logic of inductive inference, as many people hope, as indeed I once hoped. And so to be clear, I want to refute the following thesis. This is in the title of James's book, Probability. He calls it the logic of science. I want to set that aside. I don't believe it is the logic of science. I want to say only a weaker thesis. It is a logic of science, and indeed a very important one, but it is not the logic of science. Okay, that's where we're going today. Those are the two things that I'll try and do. The talk is roughly divided in half over those two claims. Okay, let's go back to the beginning and let's have a look at how the material theory of induction works. I want to take a very simple example, but I think it'll give you a sense of what's happening. Many of you will probably recognize this photograph. It's a famous photograph of Marie Curie with her husband, Pierre, and they're in their lab. This is, I take it, the place where her work on radium was done. You know the story of her discovery of radium. It was the topic of her 1903 thesis in French. This is the front page here. And the activity that led to the discovery of radium has been talked about in many occasions. She took tons of pitchblende ore, which was known to be radioactive, and over more than 3 years of painstaking fractional crystallization, she was able to separate out 1/10 of a gram of radium chloride, this much here. I take it this is a mock-up, this photo. I imagine it's probably not a good idea to hold that much radium chloride in your hand, and I will admit I photoshopped in the globe for effect, but I thought it looked good. Okay, so this is the situation that Marie Curie is in. She has 1/10 of a gram of a substance no one has ever seen before. What happens next? Well, she immediately starts announcing what the properties are in general of radium chloride. On the strength of just one sample, she starts listing off the properties. She looks at what this one sample does and then says, okay, all samples are going to behave like this. It's a little bit delicate to exactly phrase how she puts that, but one of the ways is to say that radium chloride is crystallographically like barium chloride. And so now you know the crystallographic properties of radium chloride. Okay, that was an inductive inference of enormous scope, from just one single 1/10 of a gram sample to all comparable samples. So what's happening? Well, it's an inductive inference of a particular type. This is maybe the simple gloss of it. This sample of radium chloride has crystals just like barium chloride. Therefore, all samples of radium chloride have crystals just like barium chloride. Well, what sort of an inference is that? Well, we would recognize that as an enumerative induction, one of the simplest ampliative forms of ampliative inference, going back to Aristotle. And I need not tell you, I think, that this is a rather delicate and rather fragile form of inductive inference. So it doesn't take long to realize that you have to be extremely careful using this form of inductive inference. This is one case where it works, but it almost never works. In fact, it's almost assured not to work. So if instead of running exactly this example, I'm moving my cursor over the screen. I don't know if you see my cursor. Can someone give me a thumbs up if you see it? Okay, good. So if she had not chosen exactly that, then it would not work. She could have said the sample of radium chloride is colorless. Well, maybe they're not all. Some of them have a pinkish hue to them, weighs less than 1/5 of a gram. Certainly not true for all, has crystals smaller than a millimeter, and so on. Is that the temperature of 25 degrees Celsius? Is in Paris? It was prepared by Marie Curie. No, there's no reason to think that all samples must be so. So we have a problem here. Okay. So the natural reaction to this is to say, yeah, Norton, you're being too literal minded here. You don't want to just use that simple enumerative induction scheme. You have to specify it just a little bit. So the typical sorts of moves that we would make is to say, well, let's try and restrict the A's and the B's here to things that involve projectable properties. I'm using Goodman's term here. In other words, properties over which induction can be carried out. So we might say, well, let's restrict A's to things in Curie's lab, or crystallized things in Curie's lab. Just things in the lab aren't going to be specific enough, or pure chemicals in dishes in Curie's lab. And then for the B side, we might restrict them to properties that have no spatiotemporal limits. Certain shapes may be of the right sort, colors or lack of it, sizes, all sorts of things. Okay, so at this point, just to foreshadow what's coming, some of you are thinking, well, that's a lot of fuss and bother. If you just use the probability calculus, everything works out. No, it's not going to work out that well, because every time you use the probability calculus, you need to have an outcome space, and you need to figure out what the entities living in that outcome space are. And that's what I'm doing right here. I'm trying to figure out what goes in the outcome space. You're not going to put everything in. And then when you've got that outcome space, you have to have a drenching rain of prior probabilities and likelihoods all falling out of the sky. And where are you going to get all them from? So that's just a taste of things that are to come. Okay. What I want to point out in that last example is a tendency. We started out with a rather weak inductive inference, something that generally wasn't going to work. And then we started specifying the facts more and more and more. And as we added more and more facts, the inductive inference scheme started to look better and better and better. And we started to feel we might be getting close to something that would really work. Yes, I think that's the right moral. And so I would conclude more generally, just keep calm, carry on, keep doing that, take it to its logical conclusion, or take it to the, sorry, I used the wrong word there, I shouldn't say logical, take it to the end of the process, and you will just have the facts doing all the work for you. Right? So that's what the material theory of induction says. So let's go back to Curie's example and try and see how that works if we think of facts as doing the warranting. I like to think at this moment that we could somehow stick our heads into Madame Curie's lab and say to her, Madame Curie, you've just done this extraordinary inference from just one sample to all of them. What possibly justifies this? Why is this a good thing to do? Now, I don't think she would say, oh, my dear fellow, presumably with an accent of some sort, oh, my dear fellow, haven't you read Aristotle? Right? Aristotle tells you that you can do this. This is not what she would say. She would be rather astonished, and she'd look at you and she'd say, look, I can make this inference because that's the way crystalline substances are. And how do I know that's the way crystalline substances are? Well, over the last century, work in mineralogy has been investigating how crystalline substances are, and they tell me all the things I need to know to justify this particular inference. So what she would be referring to there is something that I have loosely labeled Huys's principle. I pulled this out of the literature at the time. It is the discovery in the 19th century, after an extraordinary amount of work, that crystalline substances fall into a small number of crystallographic families. And once you've found that the crystals of a particular substance fall into one of those families, then you have a pretty good assurance that the other samples will as well. So I'm calling this Huys's principle. Generally, each crystalline substance has a single characteristic crystallographic form. find just one, and then you're authorized by that fact to infer to the case of all. Now, I want to emphasize here that this is a highly non-trivial discovery, right? In effect, to use the later language, it is the discovery of which are the projectable properties for crystalline substances. And you might think that's straightforward, but it took 100 years of work, a tremendous amount of reflections over the properties, the measurements of the properties of crystals, over work in atomic theory, and in particular, development of new mathematics in the theory of groups. So what do these projectable properties look like? Well, you've probably heard that common salt, sodium chloride, belongs to the cubic family. Now, this is something that I'd known about, and I hadn't thought terribly much about it. I thought, well, that just means that if I get a magnifier and I sprinkle some table salt on my hand and I have a close look at it, I'm going to see lots and lots of little cubes, right? What, you know, isn't that what it means to be in the cubic family? No, it is vastly more complicated than that. The cube is simply a primitive form that is used as a generator to generate very, very many shapes. And so here I've got just a few examples of the very many different shapes that all live within the cubic family. So for example, you can take a cube here and you can start fracturing off surfaces until you've chipped the thing down to an octahedron. So then an octahedron is also in the cubic family. And there are many, many other shapes, all in the cubic family. And what unifies them is that they conform with certain symmetries that come under the label of the cube. So here are some examples of octahedral salt grown under conditions of no gravity in space. So overall, there are 7 different families, and barium chloride and radium chloride belong to the monoclinic family. So now you can see why Marie Curie chose to formulate things the way that she did. Rather than talking about all of this crystallographic detail, it was simply easy for her to say, look, radium chloride behaves like barium chloride because there are isomorphisms there, they're chemically very similar, the crystals are very similar, and everyone automatically knows what she's talking about. This is just, you know, crystallographers talking to one another. So now what does this inference look like? Well, we'll just go back to the way it was before. Here's the inductive inference. Here's the warranting fact, Uy's principle. And at this point, you might wonder, well, has this ceased now to be an ampliative inference? In other words, one whose conclusion is logically stronger than what's gone into the argument. Well, that can happen. It's quite possible once you trace down these facts that you find you've lost the ampliative character of the inference when you add in the background facts. That hasn't happened here. And the reason it hasn't happened is this word generally. What generally does is to tell you that you are still taking an inductive risk when you make the inference. The inductive risk is actually quite narrowly prescribed. The inductive risk is that there is going to be some sort of polymorphism. There are substances that can crystallize into different families. So there are a few simple examples that we know very well. Carbon, I think, is the most familiar one. Carbon can form graphite, which is one sort of crystalline substance, or it can form diamond. And there are many other cases that mineralogists identified in the course of the 19th century where you would have multiple crystal forms for the one substance. So in making this inference, you're taking the risk that there's no polymorphism. Okay, I've given you one particular case of how the material analysis of something goes. I now want to show you that this is indeed quite general. So I want to try and oh, sorry, I've missed a step. So another way of putting the claim is the following. When you have an inductive inference of this type, it may appear that you are authorizing the inductive inference by means of some kind of schema that has universal pretensions. But when you look closer, I argue, you will find that's not the case. Instead, you will find a schema that looks something like this. It's going to be very specific. The A's and the B's in this version of enumerative induction will be specified to crystalline substances and the predicates that we've been looking at. And when you keep chasing back the chain of warrants, they're going to terminate in a fact. right? The warranting of an inductive inference or an ampliative inference is always going to terminate into in a fact. That's the basic claim. So let's try and generalize that a little. Once you start to think about it, I think you see it's quite easy to recognize that it's always going to be that case that way. Let me compare deductive inference with inductive inference, where I'll understand inductive inference to be ampliative inference, very general case. Here's deduction, simple deductive inference. Winters past have been snowy and winters future will be snowy. That's our premise. And the conclusion is that winters past have been snowy. Now that's an untroubling deductive inference. The conclusion merely restates part of the premises. So what warrants it? Why is that a good inference? Well, the warrant actually lives within the premises, right? It comes from the meaning of and. Right? Someone who thinks this is not a good deductive inference is someone who would be very puzzling. You would probably want to say that to them, you do understand what and means, don't you? If you put an and there, that means that each of the two conjuncts individually are going to be true if that conjunction is true. So automatically you then can have a universal schema. The schema here, I can't remember what it's called. From premise A and B, you can always infer A. So that's the sort of way that we tried to make inductive inference work. I take the probability calculus as an effort to do something like that, give us a very, very general schema. But you'll see that there's going to be trouble if we try and now give the same analysis for an ampliative inference. Let's turn that one around. Winters past have been snowy, and let's try and infer from that that winters past have been snowy and winters future will be snowy. Now, the key thing here is that the conclusion is asserting more than the premises. And as a result, it can fail. Right? So if you want this to be a good inductive inference, you need to find some sort of warrant that is going to live outside of the argument itself, the premises of the argument. And so you need to be in a world that is hospitable to this sort of inductive inference. And so this sort of inductive inference is going to work in a world where the facts are conducive to it, and they would be a world that's, say, without climate change. Whereas if we're in a world with climate change, with very significant climate change, then this would no longer be a good inference. You know, when you take into account the background facts, you'd realize, no, this is a risky thing to infer. It's not a good inference. Okay. So I'm going to argue that this is always going to be the case whenever we come across an inductive inference, simply because the conclusion asserts more than the premises and it can fail. Right? You have to be in a hospitable environment for it to be okay, and the background facts are going to determine whether that is the case. That's the basic claim here. Now we can build this up to a general argument. I'll move through this fairly quickly. I've tried at this point to establish the first premise. There are no universal inductive inference schemas. All the inductive inferences are warranted by facts, background facts of one form or another. Now, there's a possibility still that there might be some universal background warranting fact. The sort of thing that I have in mind is what Mill was looking for in the 19th century, this principle of the uniformity of nature. If nature had the right sort of uniformity, then we can always do inductive inference. I think famously Mill's efforts failed. We've been able to turn up with a factual principle of uniformity of nature. We can assert it in such a way that it's so hedged that it becomes true but vacuous, or if we give it enough content so it actually says something, there are always counterexamples and it turns out to be false. Put those two together and you get the main conclusion for the material theory of induction. It is that all induction is local, all inductive inference is local. That is, the world divides up into different domains according to the background facts in those domains, and those background facts are going to be authorizing different inductive inferences according to what's in them. Okay, so that's the basic plan. I've now, as it were, laid down the gauntlet. I'm claiming that there are no universal schemes of inductive inference, no universal formal schemas that apply everywhere. And I now have the job of demonstrating that that's the case. This is a project that I've been engaged in for a number of years. To that purpose, in 2005, I published a little survey of inductive inference. I tried to wrap my head around what does the full scope, the full universe of theories of inductive inference look like. And I was able to establish fairly well that there's a system to it. There are, I found in the end, 3 families of theories of inductive inference. I found that each one of these is powered by a particular inductive principle. We've seen the first one, inductive generalization. It's the idea that an instance confirms the generalization. Then there are others, there's hypothetical induction. That is, if you entail the truth, right? True prediction, say, then that is a mark of truth. And then there's probabilistic induction, where you have some sort of calculus that's governing things. Now, I don't know if this is capturing absolutely everything that's been said about inductive inference, but virtually everything I found could be fitted into this idea. The families each have archetypes. I've mentioned enumerative induction already, and there are other archetypes. And then there are lots and lots of elaborations. Each one has a particular problem, and so there's a need to embellish each one in order to try and repair the difficulties that each one has. Those of you who know the literature here will know what I'm talking about. If you haven't delved into this literature, you've led a happy and sheltered life, and I won't disturb your peace. So the project then is to figure out how to show that all of these accounts of inductive inference fail to give us a universal schema, and that the material theory can do better. So I've written a bunch of papers that do this. Most recently, I've got a book, The Material Theory of Induction. The complete draft of the manuscript is online. I'm awaiting publication, which is going rather slowly at the moment, but it's all there in its entirety. If you want to read it, just go to my website and download the complete book. This is a table of contents. There are 16 chapters. It kind of got out of hand. I, in fact, have more chapters that I couldn't fit in, so it's another book somewhere. The first 2 chapters will essentially just review what I've said to you now. Then the remaining chapters get on with the business of looking at different forms of inductive inference that people have used and showing how they fit with the material analysis. I've devoted the biggest part of the book to the question of whether the Bayesian system provides a universal account, universally applicable account of inductive inference, because that's the one that that I think now is most popular. For a long time, inference to the best explanation was providing very stiff competition for the Bayesian system. I think it still does, but it's kind of fading away. Okay, so let's then just talk about this one case, and you'll get a sense of the sorts of things that I'm doing. So the first chapter there is called "Why Not Bayes?" It's not a question. All right. This seems to be the default view if you're a strict Bayesian about inductive inference. You just think that inductive inference is probabilistic reasoning, right? The two are coincident. That was what was in the title of James's book, calling probability theory the logic of science. Well, my view is that this is, to a very large extent, correct. There is a lot of inductive inference in science that is probabilistic. And I could go on at great length, giving you all sorts of examples of how probabilistic inference is used in this part of science, that part of science, and that part of science. Forgive me if you're thinking that as well. Yes, I agree with you completely. But where our paths might separate is with the claim that that's all there is, right? So my claim is it's just a not always clause, right? There are going to be cases where this doesn't work, and understanding those cases is key to understanding the nature of inductive inference. So here's another way of looking at it. This I found on the internet is a map of the world of theories of inductive inference. You'll find them all present here at some particular point. And so the picture I have is that in this particular part of the map, probabilistic inference is being used because the conditions there warrant it. And then in this part, you have something else, and then something else, and then something else, and then something else. And there are boundaries between the different regions. How do you know when you pass from one boundary to another? How do you know what the something else is that should be used in any one of these different reasons and different regions rather. And I think you know the answer. The answer is the background facts are going to be doing the determination. Okay, so what's the argument for this? Well, I've already given it to you, but let's specialize it to the particular case of probabilistic inference. This was the page that I gave you before, where I laid out the basic argument that you have to trace back the warrant for an inductive inference to the background facts, and those facts have to be hospitable to the inference that you have in mind. So let's take a probabilistic example. Let's take the example of climate change and now think about it probabilistically. We take as the premises all of the present climate data that we have and related terrestrial processes and our understanding of atmospheric physics and so on and so on and so on. And then we end up with the result that there is a probability of a warming climate that is very high. Right, now you'll see immediately that this is an inductive inference. I've sort of squeezed it into the format that I had before, but you'll see it's essentially using the machinery of the probability calculus. You might say conditioning warming climate on all of this stuff. It gives you a probability close to 1. That's another way of stating it. The key thing for me here is that when you state that conclusion, I assume you're saying something factual, right? Something about the world. Right, you're not just giving me an opinion. Right? And if you're saying something factual about the world, then you're asserting more than was asserted in the premises. Right? So you can be wrong. Right? Whether you're right or whether you're wrong is going to depend upon whether the world that you're in is hospitable. Right? Now, I'm not a global warming denier. I think the facts are hospitable. I think the evidence is strong that we're getting a warming climate. And that's because our world is indeed hospitable to that inductive inference. Now, you want me to display those facts? Well, it's not terribly hard to do. I just need to go to the IPCC report, which is a very detailed examination of all the facts that then lead to that conclusion that we have a warming climate. Now, in particular, why is it that probabilistic inference is appropriate? Through the IPCC, throughout the report, they're using probabilistic inference. Where are these probabilities coming from? Well, the probabilities come in the same way that they come from die throws. Right? We don't have full information over exactly how the climate is laid out at any one particular moment. The time evolution is chaotic. And so just as we don't know what's going to happen when we throw a die, whether it comes up a 1 or a 6, so we don't know exactly what's going to happen when the climate evolves. We have a lack of information, chaotic processes to deal with, and it's out of that, in the familiar way, that the probabilities emerge. So that's fine. That works perfectly well, and I'm perfectly happy with that. But so then maybe you're wondering, well, what doesn't work? Can you give me an example of something that doesn't work? Yeah, I'll give you an astonishing example of something that doesn't work. I wonder if any of you have come across the probability of doom literature. It's a spectacular example of just someone getting it really badly wrong. So the argument goes as follows. Our world has survived for some number of years T. Now, all we're going to be concerned with is the fact that our world has survived for T. It's the survival for T years. That it's our world, and what surviving means is actually going to be irrelevant to the argument. All we really know is we have some process that has lasted for little t years. And then the conclusion of this so-called doomsday argument is that the probability that the process is going to continue on for a total of big T years, right, has the following property. That probability is greater the smaller the T is. I haven't put the full numbers up here, but let's say we pick some value of big T that's bigger than little t, and we compare that with some value of big T that is 10 times as great. Well, the first value is 10 times as probable as the second value. So it's very probable that this process is going to end sooner rather than later. Now, you look at that inference, it's a very short application of Bayes' theorem if you haven't seen it before. It's just a couple of lines. I won't bother you with it, but just trust me, it just goes through very, very quickly. Now, I'm hoping that you're all looking at that and saying, no, that can't work. Merely knowing that something has lasted 2 years does not give you enough information, right, to be able to infer anything more. If you're getting a really strong conclusion out of the type that you have, something's gone wrong. Now, I can tell you exactly what's gone wrong. What's gone wrong
it's
is
very
that you've...
difficult to hear now. There's some connection problem, I think.
Oh, are other people having difficulties?
Or maybe it's me. Can someone else share with us whether...
I heard you fine. I heard it fine.
Yeah, me too.
Okay, so it was my problem. Sorry for interrupting.
No, that's okay. Can you hear me now?
Yeah.
Okay, I'll try and slow down talking a little then, in case that will make things easier. So my diagnosis of this is that you are using an unwarranted logic of induction, and the strength of the result is simply an artifact of using the wrong logic of induction. All right. So how does that work? Well, if you're going to use a probabilistic logic, there have to be background facts that are warranting the use of that. And in this case, there are no background facts that warrant the use of probability. By supposition, there are no such background facts because we have left everything completely vacant except for this one fact. So you have no warrant to use probabilities in the first place. And if you use them, of course, you're going to get into trouble. So let's spell that out a little bit more. The conclusions do assert more than the premises. So you would need to find a background warranting fact, but there is none. But that's not to say that people haven't tried to provide background warranting facts. In fact, it's quite convenient. This literature bases this inference on a thing called the self-sampling assumption. And that assumption is the following. One should reason as if one were a random sample from the set of all observers in one's reference class. That's a fine thing to say, but I think you can see from the example that it's exactly wrong. If you do that, you will come up with spurious conclusions. So the better thing to say is don't reason as if you were a random sample from the set of all observers in one's reference class. Okay, so I think you've seen when it works, when it doesn't work. The basic idea comes down to the same thing. If you want to use the probability calculus as a logic of induction, fine with me, but there is a positive obligation on you to display the background facts that warrant its use in each case. All right? There is no default presumption that you can use probabilities whenever you want. If you try to do that, this is the sort of trouble that you're going to get into. All right, so now you're thinking, okay, if not probabilities, then what? Well, lots of stuff, lots and lots of different things are possible. And I want to give you just a flavor of what the other things might be like. I've investigated a range of different alternatives. There's a small literature out there already that looks at alternatives to the probability calculus. I'm going to give you an extreme case because it gives you a sense of how far things can move. So I want to look at the case of what I'm calling completely neutral support. Right? I want to look at a case that is like that probability of doom case, the doomsday problem. It's where you really have very, very little information. So I'm imagining some other parallel universe. We know essentially nothing about it other than there is some cosmic parameter H, right, that lives in this other universe. And we're trying to figure out what can we say about H? Well, we need to bear in mind, we know nothing about H other than there is an H. It's a real valued parameter that say goes from, you know, under 0 to infinity. Let's say that we know that much. Well, I think you can see that by simple symmetry, we would have to say that we think it's equally chancy, equally likely in the loose sense that this parameter H could be in any one of these intervals here. It's a simple symmetry principle. So far, nothing terribly exciting about that. But what I want to argue is that if we continue that sort of thinking, we get a much stronger result. We find that we have to have exactly the same degree of support, not just for each of these individual unit intervals, but for any interval that does not completely exhaust the whole continuum. So I'd write that down as a logic. If we think of each of these intervals as being represented by a proposition, then the statement would be that any contingent proposition given the evidence B, this empty background, is equal to I. I've just I for indifference or ignorance or whatever you like. Now that's the result that you come to. I'm not going to run through the arguments that take you there. I'll just give you the basic idea of where they come from. They come from invariance arguments. If you think of the arguments surrounding the principle of indifference that are supposed to be giving us a reason for why the principle of indifference is nonsense. No, the principle of indifference is perfectly fine. It says if you have two outcomes and you have no basis for choosing between them, then you should have the same epistemic attitude to them. They get the same support. There's nothing wrong with that principle. That's a complete bedrock of rationality. If it conflicts with the probability calculus, so much the worse for the probability calculus. And so if you apply that sort of thinking here, I'm calling it invariance under redescription. You'll get something like this back. Or there's a second invariance. This is invariance under negation. So I give you some proposition A. You have no idea what the proposition is. I contrast it with the proposition not A, right? You have no idea what it is. How much support do they each get? Well, it's got to be the same. If I switch them around, it's not going to make any difference. So that's invariance under negation. And that very rapidly just obliterates any interesting structure, and you end up with this complete neutrality of support. So that's a fun game once you start playing it. That one's a very simple game because you end up with a very, very simple result, and indeed a very strong one. If you want to see more examples of it, the concluding chapters of the book I just advertised has a whole bunch of examples. The one that I've had enormous fun with is the infinite lottery. I've been playing around with the logic that is native to an infinite lottery. And I know this has been used as a way to counter the idea of countable additivity. It does a great deal more than just knock out countable additivity. In that case, it knocks out almost everything else as well. And you end up with a very, very strange and a very interesting logic. And I spent some time playing around with these things and all sorts of interesting thought experiments and the like, if ever you want to chase that stuff down. Okay, but now at least some of you are thinking, wait a minute, there's something wrong here. One of the things that Bayesians have is this impressive list of arguments that show that you have to do all this probabilistically. Your credences have to be probabilistic, or whichever way you like to conceive of them. What about all of those arguments? Don't they establish resoundingly and definitively that you have to be a probabilist? Well, no, I'm going to argue now that all of those arguments fail, and they fail in the same way. And once you've seen the mode of failure, it becomes a mechanical exercise to go from argument to argument to argument and simply demonstrate why each one of them fails. So, the basic claim is that there's a circularity in the proof of the necessity of probabilities. Now, the basic structure is the following. All of the proofs that I've seen for probabilism have the following form. There are premises, and then there's a deductive inference of some sort, and then you have a conclusion, which is the necessity of probabilities. Now, this conclusion is a contingent matter. No one's saying that it's a logical necessity that inductive support has to be probabilistic. It's because you'll be assured of a sure loss, or you'll be more accurate, or your preferences won't be adhered to. There'll be all sorts of stuff like that, but it's a contingent matter. Right? And you know the way that deductive arguments work, right? If you have a conclusion that is contingent, then you must have contingent premises to get there. And the contingent premises have to be logically at least as strong as the conclusion. They might be equivalent to the conclusion logically, or they might be stronger. And you'll see from that we immediately have a dominance argument. And the dominance argument is that you take the least risk in just positing the conclusion outright, right? You commit yourself to less. And programmatically, once you realize that this is the basic structure of all the arguments, it's a very easy matter to go back and look inside the premises and ask, so where were the probabilities buried in these premises? Now, if you approach these arguments the way that most people do, you approach them with an understanding that the conclusion is correct, you know the answer, right? And so the premises are somewhat comfortable. It's a bit like watching an old cowboy movie where you know the guys with the white hats are going to win, so you don't pay too much attention to the plot because you know what the outcome is going to be. Well, you should be paying more attention to the plot here, because if you look closely inside those premises, in every case, this argument is telling you, you will find contingently encoded in the premises the very conclusion that you're supposed to be pulling out. So let me show you how that works, right? I want to show you how that works in the case of the Dutch book argument. I mentioned the infinite lottery as an interesting case of an alternative logic, and the details here don't matter beyond one point. It's possible to divide up the outcome space of an infinite lottery into three subsets, three disjoint subsets, 1, 2, and 3, written in capital letters. And the natural notion of chance that comes out of the infinite lottery says that the chance of each one of those is the same as its complement. So the chance of getting a 1, capital 1, right, is the same as the chance of getting a not 1. And correspondingly, the chance of getting a 2 is the same as getting a not 2, and the chance of getting a 3 is the same as the chance of getting a not 3. And since the whole set is 1, 2, and 3, you'll see immediately that you have what is in the Dutch book literature an incoherent distribution of, in this case, chances. And so the immediate reaction is, oh boy, that guy can be Dutch booked, right? And the Dutch book is not terribly hard to set up here. Someone who holds these chances in the Dutch book scenario is going to accept even odds bets on each of these outcomes. So you get the person to accept even odds bets on each of those. You get this table below. I won't go through the details here, because if you know the Dutch book argument, you'll see it's, this is one of the easiest cases where you can Dutch book someone. And then once you've got the person to accept those three bets, then no matter what happens, that person is going to lose. Okay, so how does that look when you then do the Dutch book analysis? Well, we have a kind of a Dutch book theorem. This is a very simple one. It's nothing like the sophistication of the general cases, but it says this: if your credences match the non-probabilistic infinite lottery chances that I've just described, and you accept even odd bets on those outcomes, that have equal credences, then a sure loss Dutch book can be made against you. Now, the standard move at this point is to say, therefore, non-probabilistic credences are incoherent. You should not have those credences, right? And that way you protect yourself from sure loss. Well, there's a small literature that says, no, this is just the wrong diagnosis of that. That's not the right conclusion to draw. The right conclusion to draw is this: if you hold non-probabilistic credences, then this sort of betting behavior is incoherent. What on earth are you thinking, betting like that when you have these non-additive credences? It's the behavior that's doing it. And in fact, once you look fairly closely at it, you'll see that built into the rules of the Dutch book scenario, right, is the probability calculus. One of the simplest places to look is the following idea: there is, by supposition, always a bet such that you would be happy to take either side of the bet. And when you filter that through the probability, through the apparatus of the Dutch book, you end up with the additivity of belief. It's quite possible to turn that off. Smith wrote papers in the 70s in which he gave new versions of the Dutch book argument in which that assumption was turned off, and came up with non-additive degrees of belief. Okay, so that's one example. Let me move on to another example. I think the most interesting argument for probabilism that's come out in the last few years has been the accuracy or scoring rule argument. I'll state very briefly what it is. If you haven't seen this in the literature, this might move a little fast for you, but let me just go through it anyway. The idea is that it's possible to vindicate probabilities without having to go to the pragmatic scenarios of Dutch books or preferences or so on. The idea is that you might have some distribution of belief, and then you can measure how accurate that distribution of belief turns out to be in comparison with what actually happens. Now, what this analysis says is if you have a non-probabilistic distribution of belief, you can always correct it such that no matter what happens, right, your corrected distribution of belief will be more accurate. Right? So it doesn't matter what happens, can be outcomes A, B, C, D, or E. If you move your credences so that they become probabilistic, then no matter what happens, your accuracy will be better. So that's the rule here. You choose accuracy dominated credences. The system that's used is a Breyer score, or more generally a strictly proper score, and from that you deduce that your credences must be probabilistic. Well, if you want the guy in the white hat to win, you don't pay terribly much attention, and that's perfectly fine. But if you're suspicious that something has just been pulled out, someone's pulled the wool over your eyes, then yeah, you look into those assumptions, and very quickly you realize that the whole game is in the scoring rules. Right? The scoring rules have to be delicately adjusted in order to give you the result that you want. And the slightest disturbance to the scoring rules will give you any result that you want. So I carried through that analysis. This is a whole chapter in the book. For those of you who know the literature, this is the Breyer score here. We have credences x1 to xr on our outcomes, and if the ith outcome obtains, we get this Breyer score. Those of you who know this will recognize the power of 2 here. That's the key parameter. So I asked, what happens if we have an n power score? Right, you replace the 2 by an n, and you get this result here. Well, you'll still get dominance behavior for most of the values of n, as long as n is greater than 1, but you almost never get probabilities back. And so here's a way of illustrating that. Let's imagine that we have the equal credence case, right, where x1, x2, up to xr are all equal. We get back the probability case if the sum of all those x's is equal to 1. And that's what's being illustrated here. If we set n is equal to 2 in the Breyer score formula, and we identify which is the dominating set of credences where all the credences are equal, they do indeed sum to 1. So that's the one additive case. But you need to have n is equal to exactly 2 for that. If you have any other value of n, you end up with a super additivity here. You add up all the dominating equal credence cases, and they come to something less than 1. Or if you have an n greater than 2, then you have the sub-additive case. If you add them all up, you end up with something vastly greater than 1. And you see the deviations are quite large here. So, in my view, that really tells you pretty much what the whole game is. It's all about picking a rule that gives you the result that you want. Right? Now, I'd like to say, well, that's the end of it. No, that isn't the end of it. It's never the end with these arguments. What happens with these arguments is there's always a yes, but. Right? And the yes, but says, okay, so I grant you that the premises of this particular argument have got built into them the probability calculus, but not to fear. I can find another argument that will give you the more reasons that are needed. So there'll be then more premises that will take you there. This I see happening across the board. Now, it's simply a matter of repeating what I've just done. Right? The basic argument still applies. Those premises are contingent for the reasons that the first ones were contingent. Therefore, they're going to have built into them the very result that you're trying to get out. And so it will continue, and you get this infinite regress of reasons that never properly ends. You might like to think of this as the method of exhaustion, because after a while you just get exhausted looking down the chain, and you just give up and stop worrying about it. Okay, so that's the story. I've been going for about 50 something minutes, so that's enough. Let me summarize in a conclusion that's a kind of pretty picture. The view of inductive inference that I'm criticizing, I'll call a dualist view of inductive inference. The idea is that there are these active universal schemas that guide the passive facts, right? It's something like pipes guiding water, right? The water are the facts, and they're being guided along the pipes, and these pipes are these fixed schemas that just live there, right? And they've been there since Aristotle, if you like. I'm arguing that's the incorrect way to think of things. We need a monist view. The idea is that there are just these facts, and these facts are capable of organizing themselves into inferential structures. So I thought a nice illustration of that are fluid systems like this. You know, fluid systems can organize themselves into stable vortices. This is a computer simulation of vortex shedding. Okay, so at this point, I can say that I've enjoyed my short time with you, and I hope you have as well. If not, you'll want to hurry away. And if you did, you might want to, if you did enjoy your time here, you might want to read a little more. The material theory of induction is available on my website. You can read the thing there, and that's the end. Thank you.
Thank you very much, John. Thank you.
I'll relinquish the screen.
All right.
If I can figure out how. There's probably a way of doing it. So how do I relinquish the screen? Oh, there it is. Ah, excellent.
Wonderful. So thank you very much. Before I take questions, in case I lose the connection, there are some problems in the connection, then Ori will take on with the Q&A session. Okay, so Ori had a question. Some other people would like to raise Arnon, Yemima, Alik. Okay, and then we'll take more. And Boaz. Arnon, Yemima, let me write down. Alik and Boaz. And then David. Okay, and then we'll see. So Ori, please.
I see many people have questions, so I'll try to be brief. Actually, I'm in the same boat as you. I think there's no general schema of induction that's valid. I think that you're right about that. Actually, if you look at 17th century inductivist views, there's always a theory of matter that sort of motivates the inductive inferences. In Bacon and in Newton and in many other cases where we have an inductive inference, it's being supported by some general idea of what matter is like. But I do have a question about the way that you are describing the view. I'm kind of have some worries about that. And the worry is this. So we have particular material facts sanctioning the inferences. So you have the inference, you have the transition from premises to conclusion, and the transition itself is sanctioned by a material fact. And it's a very strange thing to say, because it's kind of like saying the content of a proposition is telling you how to transition from one proposition to another. And I just find that description to be strange. To have a fact, to have a content of a proposition sort of tell you how to move from one proposition to another. And furthermore, if you think about it, you can always take that fact and sort of include it in a premise of an argument that's completely deductive in nature. And you yourself have written about that when you talk about demonstrative induction and how demonstrative induction is starting with particular facts and sort of moving to conclusions. And then it's not really an inductive argument, it's a deductive argument with another fact at in the premise, which doesn't sanction the inference, but it just gives you more facts to work with. So my worry is not with the general position. I think it's correct. My worry is with your characterization.
Okay, thank you. I'm not muted. Good. Yeah. Two questions. I'll try and answer quickly. First, it's in fact very familiar that facts can also authorize inferences. Think about the conditional if A then B. Right? If A then B, A therefore B. If A then B authorizes us to infer from A to B. I find that entirely normal. If I say generally X, then inductively I'm allowed to infer to X if generally X is correct. So I'm not bothered by that. I think it's actually quite familiar, and there are many more examples of that. Second case, you are correct. It's always possible to turn an inductive argument into a deductive argument by simply adding the appropriate premise, and then the argument is just seen to be an enthymeme. Of course, that's only going to work if the fact that you add itself has some factual status. Just adding I want to go from A to B, and so I'll make if A then B a premise is not going to do it. You pointed out quite correctly that I've written about a lot of cases where we thought we were doing an inductive inference in science, but we discovered that the inference was actually deductive when we looked at the background facts. The case that interested me most was the Ehrenfest-Poincaré demonstration of the necessity of quantum discontinuity in 1911 and 1912. That turned out to be simply the inversion of what we now call a Laplace transform. Poincaré actually had to invent the theory of integral transforms in order to be able to demonstrate the argument. So yeah, that doesn't bother me at all. If you're a methodologist, of course, it bothers you because it's not interesting. But if you're a scientist, it's a wonderful thing to discover that when you inferred from A to B, you weren't taking any inductive risk at all if you take into account all the other things that you already believe. Now, it turned out that that particular approach just couldn't possibly cover all cases. And so when you start to water that approach down, you end up with exactly the talk that I've just given you.
Arnon, please.
Thanks. That was very interesting, and I'm not sure if what I'm going to ask is similar to what Oli just asked, but if it is, then you can give the same answer, basically. I guess I find myself in sympathy with the negative argument that it's very hard and probably impossible to give a uniform formal theory of induction that works across a range of cases and areas. I guess what I'm not sure I see is why we should throw out the formal stuff because of that, right? So why are we forced to choose? At the very end, you describe the view you reject as dualism. Dualism sounds to me pretty good, right? I mean, we need both the formal apparatus, and there very, very well may be a variety of formal apparatuses, and we also need material principles, as you call them, empirical principles, I would call them. And we need both in every good inductive inference. Maybe people in the past did not realize this or put it this way or focused on the formal aspects, and that would be a mistake. But I'm not seeing why, from the complaints about the insufficiency of the formal formal approach, there would follow a kind of monism, as you put it in the end.
Yeah. I think I agree with everything you said. I'd retract one tiny bit, but you just articulated the view very, very nicely. I definitely do not want to dispense with all formal techniques. You might remember at one point I tried to display effusive enthusiasm for probabilistic analysis in the right places, right? And if you look at the examples in the book that I've worked up, there are a lot of formal calculi there, right? They are formal devices. So I don't want to dispense with formal machinery when it's warranted. But the point I want to insist on is that you have to supply a formal warrant in each case. So if you want to give a probabilistic analysis of something, you better give me the background fact that authorizes that, if we're being serious about this. And if you can't find a background fact that authorizes this, you better watch out. You might be doing one of those doomsday arguments. So I think that fits with what you've said. I just add one extra piece. There are going to be occasions when a formal analysis just isn't going to really do things. It's going to be a Procrustean fit. I think the example of Curie's inference on the crystalline form of radium chloride is such a case. I know you can bury that in probabilities if you want. If you look at the chapter that I wrote, you'll see efforts to bury it in probabilities. I don't think you get anything more out than you put in. So there are cases when the inductive inferences are just fairly sloppy, and that's just the way they are, and there's not much we can do about it. Is that working for you or not?
I guess I'm not seeing why this is why you describe this as monism rather than a kind of view on which in every instance we need, well, maybe not in every instance, but I'm not sure if that's what you meant to say about the Marie Curie case, but it seems to me like in most or maybe all instances, we need both a formal structure that makes, that either plays a bigger or a smaller role, and a set of material assumptions. Now, maybe in some cases, in all cases, one of these components does more work than the other, or is more kind of, involved and complicated and sophisticated than the other. But all these would seem to me like, forms of dualism, as you put it in the end, where we need both aspects, both elements.
Yeah. So again, I'll try and channel you. I think what you're saying is there's a dualistic picture where we have some problem. On one side, we're going to have formal gadgetry. And on the other side, we're going to have the facts. And there are the two things, right? What I'm saying is you've got the wrong picture, right? You're going to have some problem. There'll be a formal gadget that is going to be useful in the cases that you're thinking about. And how do we know that that formal gadget is the right one to apply? Well, there'll be background facts underneath it that authorize it. And since everything always goes back to those background facts, that's the monism that I'm talking about.
So I don't want to take up too much, but okay, wait. I'll give others a chance to ask questions. Thanks.
Okay. So thanks, and please try to be brief because we have a long list of people who would like to pose questions. Yemima, please. You're muted.
Okay, can you hear me now? Yeah, so it's been a pleasure and congratulations on your new book. And I'm not familiar with all the literature induction, so my questions will be probably very naive, but I will be brief. The first one is, where do you see yourself deviating from Goodman? Because your Curie example really reminds me of Goodman's connecting the different problems in fact, fiction, and forecast, where you say, well, there are some good projections and some bad projections. And if you project from a piece of chalk to a piece of rubber or whatever and say it will be soluble, then it's not a good projection. But if you use the notion of natural kind and project to another piece of chalk, you're better off. And what Marie Curie did was more or less, given all the background that you gave, looking at the natural similarity between those two crystals. So this is the first question. And so you need something like a kind that follows the same laws or has the same structure. And the other question is much more naive. Are you going to restrict your invariance from negation somewhat? Because if you tell me to guess a number between 1 and 100, I won't give 5 and the negation of 5 the same chance, right? I won't bet equally on them. So you have to restrict invariance from negation somewhat.
Yeah. Oh, so the second one's easy. In the setup that you've just described, we have a background fact about your behavior. And on past experience, when you ask someone to pick a number, it's roughly equally likely that the number will be anywhere between 0 and 100, when you ask them to pick. So in that case, the invariance under negation just doesn't obtain. So I very purposely cooked up an example which was as bereft of background. Oops. Someone has. Are you still hearing me, or?
Yeah, I hear you.
It says Joshua Ben Itamar has started screen sharing. Oh, okay. Sorry, I didn't mean to.
Yeah, I understand. That's fine then.
Okay. Now, on Goodman, so what Goodman says is that the inferences that we do are done out of habit, right? It's a kind of a Humean thing. They become entrenched. Now, I agree with you that we do need some way to know which are the good inductive inferences and which are the bad ones. I don't want to follow Goodman and just saying it's habit, it's what's entrenched, it's what we're used to doing. I think you're doing much better by saying we're authorized to infer over natural kinds, right? So if something's a natural. Okay, well that's fine. I have to go back and look, and if you assure me so, I fully trust you.
Yeah, I think his fourth chapter is really very misleading, because throughout the book, it gives you all kinds of hints as what a good projection would be.
Yeah. I thought it was Quine who said that you need the natural kinds to answer. But look, it doesn't matter because my answer is different anyway.
Okay.
With natural kinds, what you're looking for is some kind of a surrogate for a universal schema. You have this universal notion of a natural kind. I don't want them. I just want particular facts, right? So I at no point in the analysis of the Curie example did I say that the crystallographic families are natural kinds. Now you might say that, and that might be comfortable if someone likes the idea of natural kinds. I don't need it for my particular account here. I just need that particular fact that it warrants the inference. And in fact, I'm suspicious that it is going to be possible for us to give any self-contained abstract general theory of natural kinds. So what is a natural kind? A natural kind is a thing that, that lives in a law. Natural kinds are things that support inductive inference. And now we've come full circle, right?
Well,
so you mean I just want to say it's great to see you. The plan was I'd come and visit and come to this talk and then come to your conference, and it hasn't happened.
Well,
I'm very sad.
it will, maybe it will, but this is wonderful. Thanks.
Yeah. Hopefully we will have this conference in the near future. Alik, please.
Hi, thanks very much. So I'd like to ask, how general do you wish your claim to be? I mean, how would you like to actually claim that there are no universal schema whatsoever? So I was just wondering about the schema of most F's are G's, therefore A is F, therefore A is G, probably, yeah. So to me, is this also something you wish to claim?
Yeah.
That? Okay, so I can't see why. And
well, it's not hard to cook up all sorts of counterexamples when you have most F's are G's, and then it turns out that the next G isn't. Why do you think most F's of G is going to authorize? If you have how have you collected the most here? You know what this reminds me of very much is the combinatorial vindication of induction that I've just been looking at. It's based on that particular syllogism. Is that what you're thinking of by any chance? No, okay, so I'll leave it aside. So where are you getting, so if you say most F's that have been collected by random sampling are Gs. Therefore, the next F is likely to be a G. I agree, because the idea of of random sampling tells you you have a background fact here, that you're selecting things probabilistically. But if you aren't selecting...
Sorry, isn't this a universal schema? What you've just right?
Most people in this talk are in Israel, right? I'm not. I mean, you know, it's not a reliable schema. You have to add some pieces to make it work. The natural thing to add, and the one that people tacitly add, is that the most Fs that I've selected have been selected in such a way as to make it reasonable for me to expect that the next one is going to be a G. Random sampling is normally the way that this is done.
So I can add this as a premise, and then I have a universal schema.
No, you now have a background fact that I have a process in which I am sampling randomly, probabilistically. And if you can call that, I don't mind. You can always add a whenever to any particular rule, right? So I can add a whenever to the beginning of the Ruiz principle and say whenever the following conditions are satisfied. But that isn't what people are looking for here. You have to have a quite specific system. I mean, what does it take to have random sampling? You need a randomizer. How are you doing the randomizing? Right? You're throwing a die. Are you picking numbers out of a hat?
Thanks.
So we have still 6 people in line and 12 minutes, a bit more or less. So please try to be as brief as possible. Boaz, please.
Okay, thank you. I enjoyed the talk. And I also think that there are no universal schemas of induction. And my question will be naive. How can past facts warrant future facts? They seem like different kinds of facts. And assuming that they can, how do we know whether the future facts that they warrant are the GRU facts or the blue facts?
Okay, there are 2 separate questions there. If you have a warranting fact that extends over past and future, then it works. So the example with the Ruiz principle is such an example, and so that's how it works. I'm sorry, I'm trying to be quick here. So the second example is the GRU example. I've written on GRU elsewhere, and GRU I think actually doesn't work for a reason that people haven't paid terribly much attention to. As long as you think about simple enumerative induction, then GRU is a serious problem. But if you step outside the context of just the very specific induction that you're doing, there are going to be background facts that will distinguish. So one of them might be Yamim is a natural kind, green is a natural kind color, whereas GRU is not. So what is the escape from that? I mean, that I think basically kills GRU as a serious proposal. Otherwise, GRU is just making trouble for enumerative induction. And since enumerative induction is in trouble already, no big deal. But as a more general proposal about how we defeat inductive inference, it's now in trouble. The move at this point is to GRUify everything, right? And what I argue is if you GRUify everything, then you've ended up with 2 systems that are completely isomorphic, and that they represent different outcomes, right, has now ceased to be something that can be even expressed in the language that you're dealing with. I've just given you the abstract of a paper I wrote around 2005 or so. And so I better stop there. But the basic claim is that GRU doesn't work because in order to make it work, you turn it into a gauge freedom, and it's impossible actually to state the fact that it works. Sorry, that was an answer, but you're thinking, it's unintelligible. All right, read the paper.
This is part of my understanding, my attempt to understand, to ask the horse's mouth, about that paper. But
okay, we can talk about that. Yeah. Well, we should talk about that paper offline because no one else trust me, no one else cares that much.
I'm sorry, but no follow-ups at this point. You can continue later in private if you'd like. David, please.
Thank you, and thanks for the talk. I enjoyed it very much. I wonder that what supports inductive inferences are facts, like the facts that Marie Curie would cite about crystals or whatever. I'm totally taking your word for it, right? But it seems to me that what supports the inference is not the fact itself, but Curie's beliefs about those facts. Or anyway, I'd like to pose a kind of a dilemma here. Either it's the fact itself or it's the belief. If it's the fact itself, and really the discussion we should be having is about, extreme kinds of epistemic externalism. And I think the view then fails for the reasons those views fail. If you're just talking about the belief, this, I think, significantly de-radicalizes your claim. Because then really what we're saying is that all of this is sensitive to background knowledge, and maybe that inductive inferences, perhaps unlike some deductive inferences, is non-monotonic, and so hypersensitive to other beliefs. But we've already known that, haven't we?
Yeah, no, okay. I take the first horn of the dilemma. I don't follow the belief route for all the reasons you said. It's a bad way to go. I'm doing inductive logic. And the terms in inductive logic are propositions, and the relations among the propositions are independent of beliefs, minds, or anything else. So you're worried about externalism. Externalism is a view in epistemology. You need to have beliefs even to formulate it. I'm doing inductive logic, so I don't believe the externalism worry applies to me. I'm sorry, I'm being very terse and curt here because I've been told to. But great question. I've thought a lot about this. That's why I'm able to give such a curtain answer.
Guy, and then Danielle and Malcolm, and that's our list. Please, Guy.
Thank you for the talk. So my question is about, in the context of modern physics, sometimes the fact that you have in mind, I mean, it's hard to tell if it is a fact. I mean, it's something you could conjecture, you pose it in a mathematical language. How can you know that it's really a fact? What would count as a fact?
Oh, that's the job of further investigation. So, Hui's principle, crystallographically, was a matter of 100 years of work by mineralogists, and it's a big, messy business to unpack it. But that's the business. That's the same in physics. I mean, I don't know if there's any example in physics that draws your attention.
Of course, symmetry principles I have in mind, but
the relativity principle.
His equation, or is another example.
Okay, I've read Schrodinger's papers. They are deeply intractable. I mean, you get all this Hamilton-Jacobi stuff, and and we all argue about how we got there. But a symmetry principle, like the relativity principle, special relativity, is anchored in experiment. Einstein was very clear about that. I suppose you call gauge principle so kind of a symmetry principle. Again, it's empirical. We just know that we can't detect individual gauges. I guess because Aharonov is local, you know about the Aharonov-Bohm effect, right? And there, I think that's best understood in terms of holonomies, but again, it's empirical. So yeah.
I mean, but then what is it? The fact you could say that there is a fact in the world that it's gauge invariant. I mean, it's not.
Well, the fact has to be true for it to do the warranting. The best we can do is assure ourselves with a great degree of confidence that it is so. The warranting character of the facts is similar to the deductive inference schemas. In order for a deductive inference to be valid, you need a good schema. In order for an inductive inference to be cogent, then the background fact has to be a truth. Right? Now, it's quite possible to make bad inductive inferences because you mistakenly believe that such and such is a fact and does the warranting, and then you make mistakes. And there are lots and lots of examples of that. If you've ever looked at the continuous creation steady state cosmologies, they took as their background fact the perfect cosmological principle. Spectacular example of taking a falsity as a warranting fact and then end up with bad conclusions.
Yeah, okay, there's no follow-up. If my question is more than how do you know that it is a fact? Now, how do you know that it is true? Since it's in a mathematical language, but maybe I should stop here because
in mathematical language. Well, that's the business of physics. That's what physicists do.
What counts as a fact?
Well, things that are true of the world. You don't know what facts are. Okay.
Yeah. Okay, let's stop this exchange here, and you may continue later. Daniel, please.
Yeah, thank you. And I must say that I enjoyed the aesthetic of the presentation. It was quite nice. My question is regarding maybe some application of your reasoning to causal inference. Because in causal inference in statistics also there's the data and there's a model of how we think, a mental model of the causality we attribute to it, and then you can solve the problem. So does your claim apply also to causal inference, in your opinion?
Yes. But
okay.
Now what? Now what? I mean.
Yeah, so that's interesting. Now what? Because this is a really strong claim. Okay, thank you.
Oh, okay. Boy, I wish they were all that easy.
So last question, Malcolm, please. Are you with us, Malcolm? I don't see anyone on the camera. Maybe you left us without this question. So
no, I didn't pose a question. Sorry.
Okay. So so thank you very much, John. Despite this world, which is perhaps not hospitable for various social connections, but it is hospitable for events like this. So thank you very much for participating and for giving this talk. And good evening, everybody.
Thank you very much, John. Thanks very much for coming.
Thank you.
Thank you. It's been great. I've been very pleased to be here virtually.
Thank you. Thank you and good evening.
I'll stick around in case anyone wants to chat.